All right. Hello, everyone. Welcome to our third in the series called Deeper Talks, the SURF Seminar Series. My name is Jared Heiss. I am the Science Director at SURF. Before I introduce today's speaker, a couple housekeeping items. For those of you online, we will have a Q&A period following the presentations. And for those in the audience, you can of course raise your hand and we'll get to you with those questions. But on the Vimeo app, there's a Q&A section. If you want to put your questions into that area, we will get to those. The talk will be recorded and available after the event, and you can find that on the Institute website, institute.surf/deepertalks. And without further ado, let me go ahead and introduce our speaker. Dr. Mary Bashai is currently an experimental particle physicist at Brookhaven National Lab in Upton, New York. Dr. Bashai's research is in the field of high energy physics with a particular emphasis on heavy quarks and, as you'll hear about today, neutrinos. From 2012 to 2015, Dr. Bashai served as a project scientist for the long baseline neutrino experiment, LB&E, which led to the formation of the Deep Underground Neutrino Experiment, DUNE, in 2015. DUNE is a leading-edge international experiment for neutrino science and proton decay studies based in the US. Dr. Bashai has been a scientific collaborator on many leading experiments in the field of experimental particle physics, including DUNE, and then a whole host of other neutrino experiments, microBOON, diode reactor neutrino experiment, the main injector neutrino oscillation search, MINOS, collider detector at Fermilab, CDF2, and the CLEO experiment. More recently, Dr. Bashai was recognized by the Department of Energy. She is one of the 2024 DOE Office of Science Distinguished Scientist Fellows, due in large part to her contributions in the field of neutrinos. And so without further ado, let me introduce Dr. Bashai, who will be talking about neutrinos delving deep with DUNE. Thank you.
Thanks, Jared. Thanks to the SURF Science Institute for inviting me to give this presentation. And we are celebrating the ribbon cutting for the completion of the excavation of these massive underground caverns here tomorrow, and I think there'll be more information on the chat about that. So if most of you online may not see that, but I have 66 slides. I've spent 20 years in New York. I can go fast, I can go slow, but my goal is to interact, and it might be a little difficult online, but I'll try to interact as much as possible so that we kind of incorporate Q&A throughout. And there are many, we're delving deep, so we'll start at the shallow depths and go deeper as it goes by. I just want us to all have fun together instead of me just standing up here droning at you. So this is my outline. And like I said, I am going to skip back and forth, and there'll be sections that will be there just for you in the future if you need information. All of these are clickable links, so you can jump back and forth, and will be available after that. So I'm going to start, and many of you who are interested in this, I apologize if it's too basic. I'm going to start with very, very basic concepts, work through them together, and then we'll see as we move forward. So the best way to introduce the science that we're trying to do today is to go back and look into the history. Understand how experimental physicists, I'm an experimentalist, not a theorist, came up with the ideas and how those led to more questions and more questions and more questions as we answered questions that previously we were wondering, more questions arise. This is the nature of science. So the idea of the neutrino, if you don't know what that is, it's an elementary particle of particle physics. It's the lightest known particle, and there are about 10 billion of them go through your thumb every day. It's produced by the sun. It's produced by cosmic ray interactions in our atmosphere. We have neutrinos from, cosmic, the galactic center, from the big accelerators in the sky. So, and I believe the previous deep talk has delved into a lot of that. But where did it all start? It really started in the early 20th century when people were studying a type of radioisotope decay, and it's called beta decay. So at the time, you've heard of X-rays, which are photons. So at the time that physicists started in the late 19th century, early 20th century, the birth of 20th century physics, there were different types of radiation. And so a lot of these physicists were classically trained, but they didn't have, it wasn't very imaginative. So instead of ABC radiation, they called them alpha, beta, gamma. And these particular decays were producing something called beta radiation. Gamma radiation actually turns out to be helium nuclei, very highly ionizing. Beta radiation is actually an electron. It's not as ionizing, but they knew that, so they knew it was separate. And then gamma radiation are just basically photons that are at higher energies. And so what they do is they took an isotope, it decayed, it produced this ionizing radiation, they detected it, they measured the energy, and they know the atomic mass of the nucleus started out with, they knew the atomic mass that you ended up with. So, in 1915, Einstein said energy and mass are interchangeable, mass is energy, energy can be mass. And so they're like, okay, I know this mass, I know that mass. The difference is the radiation. If energy is conserved, then what I should see out is the equivalent of the energy of the two states that I'm looking at. But they didn't observe that. What they observed was a continuing range of energies, as we see on the plot here, instead of what you expect. For example, if you look at there are a lot of radioisotopes decaying that produce gamma rays, in particular, that are a very specific energy, right? The nucleus de-excites, emits a specific energy. That's not what they're seeing in these particular radioisotope decays. And they were going on, what is wrong with these beta decays? What is happening? Energy is not conserved, okay? And so in 1930, Wolfgang Pauli, again, a very famous, one of the founders of the 20th century of our modern physics, he wrote a letter to physicists at a workshop in Tübingen, Germany. This is the actual letter in German. I don't speak German, but if you are, you can read it. It's a long letter, but it's much shorter than most papers these days. And he says, the translation of the key parts of it is, I have hit upon a desperate remedy to save the exchange theorem of statistics and the law of conservation of energy, namely the possibility that there could exist in the nuclei electrically neutral particles that I wish to call neutrons. Remember, at the time, they knew about atomic mass, they knew about the proton because it's the nucleus of a hydrogen, right? That's the lightest nucleus. But they didn't know that the heavier nuclei were actually made out of neutrons and protons. They just knew that they were made out of multiples of what the mass of what a hydrogen nuclei is. And they know the difference in the masses, the atomic masses. And so he said, namely, that there exist in the nuclei electrically neutral particles that I wish to call neutrons. The mass of the neutrons should be of the same order of magnitude as the electron mass, and in any event, not larger than 0.01 proton masses, so 10% of the proton masses. The continuous beta spectra would then become understandable by the assumption that in the beta decay, a neutron is emitted in addition to the electron, such that the sum of the energies of the neutron and the electron is constant. So they knew that beta decay is an electron, which is an ionizing particle. But this particle had to be neutral. It had to be ionizing, so we don't see it. And so this is the explanation for why the spectrum is continuous. Now, by looking at the maximum energy that the electron is carrying away, they also, and they know the mass of the atomic mass of the initial nucleus and the final nucleus, that gives them an idea of the mass of this particle. And that's where there was this idea that it's significantly lighter than a proton, okay? It's the same order of magnitude as the electron mass. That's the limit of the precision. And then he said, I have this great idea, groundbreaking idea in particle physics, but I cannot appear in Tübingen personally because I am indispensable here in Zurich because of a party, on the night of the 67th of December. So I gotta go to a party, guys. Sorry. Here's the letter. Figure it out. So we don't all just hang out in. It's amazing the number of great ideas that physicists got while they were out hiking or biking or sitting around dinner with a glass of wine. So doesn't always happen in the labs. So just to set, you'll see a lot of symbols we throw around. This particle is now what we call the neutrino because the neutron was discovered later in the 1930s, and it had the mass of a proton. It didn't have 10% of a proton mass. It did not, its mass was too big. It's actually 0.1% heavier than a proton. And so it's not neutrons. And so Enrico Fermi came around, and he's Italian. He says, it's a little neutron. It's a neutrino. So that's what we call the neutrino today, is this invisible mass particle with low mass that is emitted in beta decay. And we use the symbol, the Greek nu, for that. And for neutral particles, whenever a particle is its antiparticle, if it's neutral, then we put a bar on it to indicate that it's a neutral particle. So if you see neutrino with a bar on it, that's the antineutrino, and we don't know yet whether they're the same thing. A photon is the Greek gamma. An electron is an electron with a minus sign, because that's the charge of it. An anti-electron, we sometimes say anti-electron, we say positron. That's electron with a plus sign. That's an E with a plus sign. If you use small p or small n, that's proton or neutron. But a lot of time we use big N, and that means either a nucleon, a component of the nucleus, and it could be either a proton or neutron. Now, like I said, we are very sloppy. We express mass in terms of energy. And so our yardstick is the mass of the proton. So the energy that an electron goes traveling from one side of your AA battery to the other is an electron volt. It's 1.5 volts. Electron goes through 1.5 volts. It gains an energy of an electron volt. That's the basic unit of energy we use. And you can look up how many joules that is in terms of actual mechanical engineering energy units. So our yardstick is 1 billion giga-electron volts is the energy equivalent of the mass of a proton. Just keep that in mind. Giga-electron volt is energy equivalent of the mass of the proton. And somewhere on the internet I found that 1,000 giga-electron volts is the energy of a flying mosquito. I don't know how anybody measures the energy of a flying mosquito or whether this is right. It could be one of those things on the internet that's wrong. But nobody's come up to me after my lecture and said, that's not right. Okay. So, we now have an understanding of how, so now we have a neutrino. We have radioactive neutrons that decay. We know now radioactive decay is caused by a neutron that decays to a proton, emits, which stays in the nucleus, and then it emits the electron, which was the beta radiation, and the invisible neutrino. In the 1930s, there was a whole theory that was developed that allows us to calculate the probability of all of these interactions. And the theory basically says, this came about from Enrico Fermi and of course Richard Feynman, who from the quantum electrodynamics point of view. And in this particular theory, it says that basically what's happening is we have a current, a weak current. We have electromagnetic current. The photon is a propagator of the electromagnetic force. We have a weak force, and so they say for this weak force, there's a current, and there's a charge carrier associated with that, or a current carrier associated with that. And it actually turns out for the weak force, which is responsible for this radioactive decay, we have two of them. One is a charged particle called the W boson, and one is a neutral particle called the Z boson. We'll get back to the Z boson later. And these Feynman diagrams are actual calculational tools. So you can see that you can draw a Feynman diagram where a neutron decays to a proton, electron, and a neutrino, or you can have a neutrino interact with a neutron to produce a proton and an electron. And again, the intermediary is this W boson, or you can have a neutrino interact with a neutron or a proton, transfer some energy through this interaction. There's no charge exchange. So in that case, it's a Z boson, which is neutral, that's involved, right? So how many people watched the Oppenheimer movie? Raise your hand. I don't know, online, raise your hand. Okay. So it's a 3.5-hour movie. There's the guy who came up with all these Feynman diagram and quantum electrodynamics and so on. He's in that, go find the scene where there's a guy sitting, he's the one slathering his face and wearing the dark glasses or beating the bongo drums. That's Richard Feynman, and he wrote a book called Surely You're Joking, Mr. Feynman. For those of you who are fans, look it up. It's hilarious. He was quite a character. Okay, a little exercise. Everybody wake up. So we know neutron decays to proton, produces an electron and a neutrino. Now I have a bar on here because it's an anti-neutrino. So we have physicists talk about conservation laws. Neutrons and protons are part of a family of particles called baryons. Electrons and neutrinos are part of a family called lepton. Whenever you see a neutron or a proton, you give it a quantum number, baryon quantum number of 1. If it's an anti, it's -1. And it turns out that conservation laws, these are observational laws. We don't have fundamental theories that will tell us what exists, is that baryon number is conserved and lepton number is conserved. So in this interaction, I start out with a neutron, I end up with a proton, baryon number 1, but I have lepton number of 0. So that electron is accompanied by an anti-neutrino, which has a lepton number of -1. So now we're all going to do physics. We know this happened. We've postulated neutrinos, now we have to detect them, and our theory tells us how to do that. A neutrino could interact with a neutron. So in this particular formula, I have a neutron plus a neutrino. So I have baryon number 1 on the left side, lepton number 1 on the left side. I have to then end up with a baryon of 1 and the lepton of 1. So a neutrino interacting with a neutron gives me a proton and an electron. Everything. You're doing physics now. We don't need the quantum chromodynamics, but all right. So this is the first thing we can wake up. What do you think what happens if an antineutrino interacts with a proton? You can start from the formula on the top. Tell me what should be on the other side. I don't know if anybody's online trying to guess that. Can anybody in the audience guess? Okay, positron, and what else? And a neutron. That's it. Magic. All right? So, when a neutron radioactive decays, produce what? Antineutrinos. Antineutrino interact with a proton to produce a neutron and a positron, an anti-electron. Now I can find neutrinos. So, go back to the Oppenheimer movie. The original proposal was to actually detect neutrinos during the 1950s because they were doing atomic bomb tests. And it wasn't because you needed to, test to fire an atomic bomb. The original proposal was, okay, we need to go really deep underground, to really shield it from all the radiation, has a very big detector, okay? That's not very practical. So then the same people, Fred Linus again, and now Clyde Cohen, decided, okay, detecting neutrinos from the radioactive decays that happen after the chain implosion maybe we should go to a nuclear reactor. That's where we have controlled chain reaction, followed by a huge chain of radioactive decays. Turns out there's about 2,000 decays in the chain that follows the fission reaction in a reactor. But that's emitting neutrinos. It's emitting antineutrinos, remember? So, but I know from my theory of weak interactions that an antineutrino plus a proton produces a neutron and a positron. Now, positron is antimatter. So any detector is made out of matter. It will annihilate with the electrons in whatever matter my detector is made out of and produce photons. But a lot of things are interacting in my detector producing photons. So the detector they chose is filled with water with cadmium chloride in solution. And the trick here was I have cadmium. And the reason is that I have both a neutron and a positron. The positron annihilates, gives me the light. The neutron, this particular cadmium, it will be absorbed by cadmium. It becomes a different isotope, which is excited. It de-excites and emits another photon. And that happens with a known characteristic time of about 5 microseconds, 5 millionths of a second. So I will get a photon from the annihilation. I will get a photon from the de-excitation of the cadmium because it absorbed that neutron. And that is uniquely a signature of neutrino interaction. And, you know, there's interactions in the detector all the time from background radiation, but they could actually turn on and off the reactor, which is what they did, right? And they knew how many neutrinos to expect. So this was the first evidence and a signal of neutrinos, and it really tells us how to detect neutrinos. It lays out, we always detect neutrinos by interactions with protons, antineutrinos with protons, and neutrinos with neutrons, and you produce either a proton and an electron, or a neutron and a positron. And that is the fundamental way we detect these things. So it took until 1995 to share the Nobel Prize, because for a while people just did not believe the data. You have to confirm it. So I'm going slow because tell me if you want me to go faster or if this is, people are engaged. I think, okay. Another important thing. So that they were also the first to estimate the interaction strength of neutrinos. The cross-section, we use this number in physics called cross-section that gives us an idea of what the interaction says. It's 10 to the minus 43 centimeters squared per nucleon. Okay. If you're a physics undergrad, the way to solve all your problems is to balance the units, even if you don't know what's going on. So this is my hint to doing your introductory physics homework. Balance the units, even if you're not sure how the formula should go. So to understand what these numbers mean, let's do a simple calculation. What is the mean free path, which is the path a neutrino will take until it interacts? In lead. So the neutrino has so the way we do this, we use the sigma cross-section, we'll multiply it by the number of nucleons per centimeter cubed. Now, the density of lead is 11.4 grams per centimeter cubed, but I need to know how many nucleons there are in there. So if you're a physics graduate student, this is a magic number, or chemists, you should all know this. Introductory physics classes. Does anybody want to hazard a guess? How do I calculate knowing the density of a material in grams? How many nucleons are there in a gram of material?
6.02 times 10 to the 23rd.
Okay. I'm going to ask you what your background is. But yes. Avogadro's number. I don't know if there's any comments online, but you know, if you're online, just put it in there. All right, let's put it all together. I have 10 to the minus 43 centimeters squared per nucleon. Put it all together. I end up with a mean free path of 1.5 times 10 to the 16 meters. And then, how many light years is this? How does it compare to the distance to the sun to the moon? If you were students, I would have you on doing Wikipedia searches right now. But since we don't have time, I'll give you the answer. So, if you fill 100,000 times the distance of the Earth to the sun with lead, a neutrino will go through with very small probability of interacting. That's the mean free path. In comparison, a mean free path of a proton in lead is 10 centimeters. Questions?
Isn't that 6.022 times 10 to the 23 nucleons per mass of atomic mass of lead in grams?
It's also the number of nucleons in a gram of material. Yeah. So it's also, yes. And so that's how we calculate how many, and here I'm using nucleons as protons or neutrons together. All right. So anybody freaking out about, you guys are making neutrinos, just remember, they just go through. The next important step, and after that I will jump to DUNE, a little bit about DUNE, is producing neutrinos from an accelerator, and this happened at my laboratory, which is Brookhaven National Lab, which is, people were studying neutrinos from the sun, we were studying neutrinos, which is rather difficult, but we want to do it in a controlled way. And so they proposed, the first successful accelerator neutrino was in at Brookhaven National Lab. There's a proton accelerator, and the proton will hit a target. It produces a hadron, which is a meson called a pi meson, which is made out of quark anti-quark pair. And then just as in the radioactive decay, neutron decays to a proton. It's actually a quark in the neutron that is changing from one quark to the other. Same quark in the pion also decays exactly the same way, but in this case it produces a neutrino and a muon. Radioactive decays have always got neutrinos that produce associated with electrons, antineutrinos associated with electrons. In this pion decay, 99.9% of the time it goes to a neutrino and a muon. A muon is a sister of the electron. It's about 200 times heavier than the electron. And we're bathed in muons from cosmic rays all the time. So the question were, are these two neutrinos the same? All right, so we know that from the discovery of neutrinos that a neutrino produced from radioactive decay with an electron, when it interacts, it's an antineutrino, produces a positron. Is the neutrino from this one also going to interact and give us an electron? So they put a detector, so there's a lot of, there's a lot of pions going out that haven't decayed, there's a lot of other, the target, is breakup of the nucleus in the target, and so they put this detector, which is basically high voltage with some gas in between, and it sparks when an ionizing radiation is produced, behind a lot of steel and concrete shielding, and then they looked at the signals. And I think that the three guys who did this were Liam Lederman, Mel Schwartz, and Jack Steinberger, and I believe this is Jack Steinberger, but I may be wrong. And you can see over here that the interactions are producing these long tracks. Turns out these long tracks are muons, because it's 200 times the mass of the electron. It tends to punch through. It's ionizing radiation like an electron. But when an electron is produced from an interaction, it will hit other electrons. It produces what's called a shower. It doesn't produce a straight track like this. It produces like a whole bunch of charge, and it looks like a shower. But also the interaction, if it's a neutrino, it's invisible, comes in, and suddenly there is an interaction near a detector, and you get these signals. And they were able to calculate the energy of the produced muon, because the muon starts here and ends here, you know exactly what its energy is. If it starts here but exits the detector, you know the minimum momentum of the neutrino. This is actually the data. How many muons from the interaction, how many electrons from the interactions, and they can turn off the beam. Very easy. Turn it off, nothing there. Turn it on, flash. And you can look from conservation of momentum that the tracks are in the direction where the proton beam is coming in. So proton beam comes in, conservation momentum neutrinos produce preferentially in the same direction. And that's where they put their detector, and that is where they see preferentially the momentum of the outgoing particle. So they found that most of the interactions that were clearly neutrinos were of the type that produced a muon. So they're like, that's not the same neutrino, like the neutrino that protrudes from radioactive decay that we detected through its production of a neutron or positron. And so it's the two neutrino experiments, sometimes called the two muon experiments. And so this was the discovery that just as we have electrons and muons, we also have electron neutrinos, muon neutrinos, and then we eventually discovered that there's even the tau, which is 3 times heavier than a proton, which is also a lepton family, elementary particle, a much heavier sibling of the electron. The other important thing is, how many neutrinos are there? How many families of particles are there? And this is where our collider, a lot of people don't quite appreciate it. So before we had the Large Hadron Collider, which collides two very high energy proton beams and discovered the Higgs particle, there was an electron-anti-electron collider there at multiple hundred of giga-electron volts center mass, and this was called the LEP collider. And it's the same physical space that is now housed the Large Hadron Collider at CERN. And so in the 1980s and 1990s, we were using colliders to collide electrons and anti-electrons at hundreds of GeV, giga-electron volts of energy. And then you measured the cross-section, the probability that interactions happen when this happens. And you scan. And what they were seeing was that the cross-section of the interaction would increase. And this is how we actually discover a lot of our particles in colliders. So here's your cross-section number. Here is the energy of the total energy produced by the collision, and you get this resonance effect. And the resonance effect happens when a particle of this mass is produced. That's how we discovered the particles. That's how the W and Z bosons were discovered exactly this way, and that was a Nobel Prize that went to Carlo Rubbia for that discovery. And so in this particular case, this was the Z boson. Remember our Z boson? Neutrinos come in, interact, exchange a Z boson, neutrino comes out. Well, the Z boson decays to quark, anti-quark pair, electron, anti-electron, muon, anti-muon, neutrino, anti-neutrino. And the width of this resonance is proportional to the number of particle-antiparticles it can decay to. So the more particles, the wider it is. So everything else, quark, anti-quark, they can measure. They're all charged particles. The neutrinos, the mass of these detectors, they're pretty big detectors. They're just not big enough for things that go through a light year of lead. Through 1.5 light years of lead. So those neutrinos are kind of invisible. And so they call this the invisible width. And this is the prediction if we have 2 types of neutrinos, 3 types of neutrinos, 4 types of neutrinos, and the points here are the data, and you can barely see the statistical uncertainties on those numbers. And so this is where we infer the number of neutrinos that couple to the Z, we call them active neutrinos, that interact through the weak force, or 2.984 minus 0.008. It's also our only hint of this magic number 3 for why we have 3 of everything. 3 families of quarks, 3 charged leptons, 3 neutral leptons. So this is a fantastic and beautiful measurement, and it's easy to understand, and that's why we have. So I'll stop here and see if people do have questions so far.
So that experiment then is really why we do, Yes. So that experiment is really why we do everything in sets of 3s. And
That experiment tells us we have, there's something special about 3. And that's in this particular case is that we have 3 families of leptons. But we also know that there's also, you probably heard that in the previous deep talk, that our understanding of cosmology has improved. We now have a very strong model for understanding cosmology, and that includes in it how many different types of neutrinos are interacting. Active neutrinos, they're called. It's not there may be more types of neutrinos, but not the ones that do the weak interaction. And that also gives us a number that's 3 now. So something special about this number. But again, that's why it's called the standard model of particle physics. All of these are observational symmetries, observational numbers, and that's why it's not a fundamental theory. It is a model, right? Because we do not have a fundamental theory that tells us why there's something special like this. This is now our standard model. Now, if we go back very, very quickly, remember that we had a very good hint of what the upper limit on the mass of the neutrino is. So right now we have the experiments are putting that use tritium beta decay and look with incredible precision at the maximum energy that the electron carries out, we put an upper limit on the mass of the neutrino of around 0.4, half an electron. What's the mass of the proton? And someone else answer. Our yardstick in electron volts. How many electron volts is the mass of protons? Maybe somebody online. It's 1 billion electron volts. Okay. It's 1 billion electron volts. So, we knew neutrinos have flavors. We knew neutrinos, we also know from the very famous Ray Davis experiment, which I don't have time to mention, that neutrinos are actually have mass because they change from one flavor to the other. This is because we found a deficit of electron neutrinos from the sun when we looked for those here at what used to be called Homesick Mine in the 1960s. So this is where the DUNE experiment comes in. We know how to make neutrinos from proton beams, and they're mostly muon neutrinos. We knew from all these studies of solar neutrinos, including the incredible experiment here, that neutrinos from the sun, there seemed to be a deficit, but that was because we were only looking for electron neutrinos, and when we had experiments that counted all the neutrinos from the sun, and we predicted how many there were, we found that they're all there, but they're not electron neutrinos anymore. So this is going a little deeper now. So this is probably, last year of undergraduate physics in the US, quantum mechanics, introductory quantum mechanics, where if I have neutrinos of 2 flavors and 2 different mass states, the probability it's a quantum mechanical interference, right? So it's quantum mechanics. I don't expect people to know quantum mechanics, so I'm not going to go through this. You can go through this if you want a little bit more. The probability that an electron neutrino of type flavor A, electron muon tau, goes to B, if it's only 2 of them, just to make things simple, is there's a probability amplitude, and we usually use these, we call them mixing angles. And I'll tell you why they're called mixing angles. But it's basically a way of parametrizing the probability amplitude. That's why you see this sine squared 2 theta. It's just an amplitude. And then when the distance a neutrino travels divided by the energy, and the difference in the mass squared of the 2 states, you will be able to look at the probability changes from one type of, you will see this quantum interference pattern, and this is distance in kilometers per giga electron volts. This is quantum mechanics on a kilometer scale, right? So this is the probability that I will see a neutrino that starts out at type A, at a distance with a giga electron volt of energy at a distance so much in kilometers, B, and then the probability goes down and it comes back up again, and that depends on this value. And then the mass difference squared. So when this becomes a 1, sine becomes a 1, that means this value is pi over 2. That tells you what the mass difference is. And that's how you can look at these oscillation of neutrinos and extract the mass difference. So this is the experiment I was talking about, and I don't have time to talk about it. It's the discovery that this is a proposal. This is something that really happens. But I want to then go to this data over here. So now what we have over here are muon neutrinos from the atmosphere, the probability that they are still muon neutrinos measured in this large tank of water called the Super Kamiokande experiment. And next door, a large tank of scintillator that was looking at anti-electron neutrinos from reactors and measuring their probability as a function of the distance divided by the energy in terms of, and so these 2 experiments sit side by side in the same mine. And we know that the difference in the mass squared from our quantum mechanics can be extracted by 1 over 1.27 pi over 2 E in giga electron volts over L. So you can actually take this data You can go to this lowest point and you can look at the distance over energy of this interval here. You can look at the distance of an energy over this interval here and write down what the mass difference is. Yeah. Okay, I have 5 minutes. 5 minutes until Q&A. All right, that's fine. And what we found out is that we have these numbers, and you can read them off this plot. And when I do lecture, I ask the students to actually do that. So one difference gives you 2.4 10 to the minus 3 eV squared. One gives you 7.5 times 10 to the minus 5 electron volt squared. So what does that tell you? There's at least 3 different mass states because I have 2 differences. So that's where it all comes from. And they got a Nobel Prize for this. So now this is the whole, so all these numbers, you'll hear us talk about all these mixing angles. We have 3 different neutrino masses, all with different amounts of electron neutrino, muon neutrino, and tau neutrino flavor in them. If I say sin squared 2 theta 1 3, that means that it is the amount of electron neutrino flavor in mass 3, which is tiny. Okay, whereas the muon and tau neutrino flavors are almost exactly the same, and that's given by this number over here. And these are the mass differences squared. And this is our quantum mechanical states and how they mix together. Okay. Just remember, again, these numbers that we throw out there are just telling you the fraction of the different flavors in the different mass states. So I'm going to now come to talk very quickly about DUNE in a few minutes. But basically what we now start to do is we look at the oscillation of muon neutrinos to electron neutrinos. We look at that oscillation pattern, and that oscillation pattern is governed by all of these numbers, and it's also governed by a phase. And if that phase, and so this quantity over here has all these numbers in it, which we all know, but we don't know what this phase is because we have 3 quantum waves propagating. And so we know that this number here, which is a magic number that theorists tell me it has to do with matter-antimatter symmetry, is 3 times 10 to the minus 2. There's this mixing in the quarks. We know all the numbers in the quarks, and there is 3 times 10 to the minus 5. And so this, we know there's matter-antimatter symmetry from the mixing in the quarks. And we think that but it's too small to explain the amount of matter we see compared to what we think was produced at the Big Bang. What gave matter an edge over antimatter, even though they were produced the same amounts as the Big Bang? So now all of our hope is this, and is that we measure this one last number here, and with high precision, and this number, and if this number here is close to 1, say, then you have 3 orders of magnitude larger asymmetry. So I'm going to very quick, and this is where the DUNE experiment comes in. There's a lot more I could talk about, just to give you a flavor of it. We can look for extra neutrinos, and so this is like the probability of an interaction if you add a 4th neutrino state, and you do experiments where you look at this probabilities very close to where the neutrino beam is and very far to the neutrino beam is. And you can see that the probability of muon neutrinos oscillating and, to muon neutrinos or tau neutrinos or this 4th neutrino, it basically adds wiggles on these patterns that you see. And that's where this is. So the deep underground neutrino experiment is a neutrino interferometer. We start out with a neutrino beam produced exactly the way as I told you it is. That from the proton accelerators at Fermilab, it travels 1,300 kilometers. There's a set of detectors at Fermilab, and there's the set of huge detectors whose caverns we just finished that we are going to start building next year. Here, in the caverns we just finished. And it's 800 miles. The neutrinos travel through the Earth. 99.9999999% of them don't interact. There's something that 1 out of a billion might. And then they will interact in our massive detectors here. The detectors are about 17 kilotons, there's 4 of them, and 10 kiloton is the actual volume that is instrumented. And the beam is 2 megawatts, that's the power in the neutrino beam. And we're going to look for these oscillation patterns, and we're going to look for extra wiggles that might say new physics is happening. And you can go and click over here and see what type of new physics we can look for. We're also going to look for proton decay. Every time you have large amounts of protons, you look for proton decay. Or you can look for neutrinos from the sun or neutrinos from supernova. The scientific collaboration has about 1,500 members total, 1,400 active. We have 37 countries and 209 active institutions. And this is a picture of all of us from one of our record-breaking posts. I put this in here, it's 2023, it's a year ago, because that was the meeting right after COVID shut down. And you can see, we had 370 this January at CERN, in person, showing up. So this is record. Our annual meeting at CERN, always we have the most number of people come. As I said, the caverns are ready. Tomorrow's the ribbon cutting. I think that you'll probably have deeper talk about all the technologies involved, but I want to point out one piece, 1 minute to talk about it, that people rarely talk about. And that is the incredible technologies that we use to produce neutrinos. We need a very, very intense neutrino beam, which means we have to start out with a high power proton beam. The accelerators produce a proton beam that we are hoping can be upgradable to 2 megawatts. That's the average power. How much wall power do you think is needed to produce a 2 megawatt proton beam? If you go and search under Fermilab sustainability plan, they will tell you what the projected power consumption is. And the projected power consumption is 800,000 megawatt hours. So almost 800,000 megawatt hours. That is about the power that all of Rapid City annual electrical power used by Rapid. I haven't checked, but that's about what you would expect for a city of 100. So it's 100 megawatts to run this accelerator complex. So that's another complete deep dive in and of itself. And it's very, very challenging to put 2 megawatts on something that's this big, which is the target. A lot of material science goes into the design of this target so that it doesn't fall apart every time a pulse, and it's 2 megawatt average, 2 megawatts in 10 microsecond pulse. The science and engineering of these proton targets don't get enough visibility. But here's our detectors, and I do want to finish with one thing. Could we play, please? So there's a prototype detector sitting in a neutrino beam using the technologies that we have in DUNE, and it's sitting in the just play the GIF. Yeah.
So this stuff right here.
Oh no, I think yeah. And this is real data from the prototype detector that uses this liquid argon technology. And this is the neutrino interactions. You can compare that to what the picture I saw from the 2mu1 experiment. So you can see event number, you can see the time over there. So we have the first neutrinos in this big, massive, $3 billion experiment. Currently in the little detector that's sitting, our prototype detector. It's about 2/3 of the size of one of the detectors we'll end up with from that side. And that's it. If we need to deep dive more into the technologies of DUNE, I'll be happy to.
Okay. Thank you, Mary. Thanks for taking us along on that fabulous journey. We don't have a lot of time for questions, but we do want to at least open it up for one or two. Any in the room that we can get to? Any curious neutrino questions? What online?
I have one.
Go ahead, Chad. Here, let me bring this so that folks online can hear you.
How do you use the technology to tell the difference between an electron neutrino, a muon neutrino, and a tau neutrino?
Tau neutrinos are what I want to do. But this is, So we have detectors that use, so our detectors are the neutrino comes in, it interacts, it produces an electron or a muon or a tau. It also, at these energies, because it's a few giga-electron volts, can break up the nucleus it interacts with. And when you break up the nucleus, E equals mc squared, you can also have pi mesons being produced, multiple protons ejected, multiple neutrons ejected. Protons, pi mesons, they're all charged particles. So you can see we're on slide 55. You can see, for example, we have our detectors, all the charge readout planes. You have an electric field, all that interaction produces ionizing radiation that travels to something that looks like your camera sense plane, except it's made out of wires because it's, it has to be 10 meters high. And it's 66 meters long is one detector, so we have to image on very large size. And we collect and we create these images. It's a 3D image, but these are the 2D projections. The charge readout planes, the charge planes are 2D, but the detector we actually reconstruct in 3D. Here is the simulated interaction of a 3 giga-electron muon neutrino, and you see the long muon track. And then this looks like a pi meson was produced, a neutral one that then decays 2 photons that then produce electron showers, electromagnetic showers. This is an electromagnetic shower here. This is where the primary particle produced is an electron. So also an electromagnetic shower, but a single one, not the two we have over here. And another, you see over here probably a proton and maybe a pion from the breakup of the nucleus. And so we actually use a combination of computer processing of these images, and we also use machine learning to identify features here to tell us this looks like, it's easy to say this is a muon track, but let's say this track was shorter, and you had this electromagnetic shower from a neutral pion decay over here. Then it becomes difficult to tell this from this. But that's where we employ, we enhance our computer-aided reconstruction and identification techniques with actual, and we have been able to verify this simulation because here, for example, we have a pion comes in and interact this charged particle beam at the CERN, where the 5% prototype detectors sit. So we verify that, and we then feed that back into our simulation, and we use that to train our artificial intelligence programs to be able to tell apart. This is easy. I can do this by eye. I can scan 1,000 events by eye, and some of them are much harder.
Great. Other questions?
Yeah.
So I work here at the visitor center, and my role with SURF is a lot of public interactions, people who have really never heard of this at all. And the question I get the most is, why embark on this research? And I know I have the answers that I give to the general public, but I'm curious if you're speaking to I'm not a physicist, speaking to a non-physicist, why invest the resources and materials into this research?
Yeah, so I have one slide where I show, what neutrinos and total. So personally, okay, if I want to know, I can study quantum mechanics. Come on, it's beautiful. I mean, it's looking at quantum mechanical interference. It's an interferometer. It's quantum entanglement. It's fantastic in that way, and so that's just learning about that. Learning more about neutrinos, we can also use this to watch out for supernova exploding and see what's going on in the supernova, which I can't see. I only see it after it explodes in visible light. But the actual mechanics of the explosion give you a particular signature in these detectors, and this is what it looks like. See, this is the number of neutrinos, the energy neutrinos, which is ergs per second, as a function of time. And so you can see, as a function of time, this is the events in neutrinos from a supernova, close by, about 15 kiloparsec. And you can see all these features in the time and in the time spectrum that you can allow them to look at the dynamics of a supernova. And the detectors are so good you can actually probably point back into the sky to where it happens. So it tells us, it can help. Theorists tell us, well, we don't know. If there's matter-antimatter symmetry, why am I here? There's matter-antimatter symmetry maneuvers. I made up carbon and hydrogen. That came out of supernova explosions, okay? That's where all the heavy elements came out. They came out from the death of stars. So not only do I need more matter, but I also need the stars to explode. and then we can get the heavy elements that we got. So that's the answer I give. When I give these lectures to students of more particle, I have a whole list of technologies. So I spent some time talking about those proton beam technologies. The high power proton beam and being able to use them are used to produce neutrons for research. They're used to produce neutrons for radiotherapy. There are people looking into, as we increase the proton beam, the technologies we produce to make it possible for us to operate megawatt proton beams. You can actually use that to treat spent nuclear fuel, if you can go up to 5 megawatts, so that you make it less dangerous. You take the long-lived isotopes and create more shorter-lived isotopes. You can do that. There are people who are looking at it to drive nuclear reactors instead of using uranium. That's the part of it they're interested in. The geologists are using neutrinos from the Earth to study the composition of the Earth's core, because the heat in the center of the Earth is produced from uranium and thorium. And so a lot of these big, deep neutrinos, not our experiment, we're not so sensitive to that. The bigger one, the other neutrino experiments, especially non-proliferation. The technologies Rines and Cohen's used to discover neutrinos, we're now going back. We can so precisely measure the spectrum of neutrinos from a nuclear reactor that we can tell you which fuel is burning. So we did all this because we wanted to understand why we're here. Some aspects of why we're here. But the feedback goes the other way. And whether it's kind of blue sky research into new ways, new types of nuclear reactors that don't have proliferation, don't produce plutonium, or whether it's using the accelerators for radiotherapy, or or studying we can study the atmosphere with all the muons that we produce here, the weather in the upper atmosphere. There are a lot of things that come out of it as well. But primarily it's driven by the big questions in our universe.
Very good. Well, with that, I think we should wrap up. Let's thank Dr. Bashai again for a fabulous talk. A few last-minute housekeeping items. I'll trade your places real quick. This talk, as we mentioned at the outset, is available online at the institute.surf website. Next month's Deeper Talk will be September 11th, same time, 9 a.m. Mountain Time. And the topic will be carbon sequestration, featuring speaker Dr. Scott Beeler from School of Mines in Rapid City. Last but not least, take a quick second to fill out the survey. I think the survey is available online for those in the room. There are some QR codes as well. It'll give us important feedback that we can use as we plan future events. And thanks once again, Dr. Bashai. This was fabulous. We're really excited as DUNE, that DUNE Caverns are done and DUNE Science is coming not too far down the line. So thanks again to everyone for participating, and we'll talk again.